Today we'll be talking about inequalities. So we'll be mostly talking about AMGM inequality, Cauchy-Schwarz, and some examples. So the AMGM inequality states that the arithmetic mean of a set of numbers is greater than or equal to the geometric mean. So in this case, the arithmetic mean is the sum of all the numbers divided by n, where n is the number of numbers, and the geometric mean is the nth root of the product of all these numbers. So the equality case in this inequality holds if and only if all the numbers are equal. We go through a quick proof of AMGM. So it is well known that the square of a real number is always non-negative. So in particular, the square root of a1 minus square root of a2, the square of the whole thing, is non-negative. So a1 plus a2 divided by 2 is as at least the square root of a1 a2. So that means that for n equals 2, we have shown that the arithmetic mean is always greater than or equal to the geometric mean. So we are going to use this idea to induct on k, where k is the exponent of n, and show the AMGM holds for all powers of 2. Now suppose that for k greater than or equal to 1, we know that AMGM holds for 2 to the power of k, n equals 2 to the power of k. Then we have the left hand side in AMGM inequality for 2 to the k plus 1 is actually this expression, and we can split it into two different sums and apply the AMGM inequality twice, since we have already shown that it holds for 2 to the power of k. We obtain the following expression after using the AMGM inequality on two numbers, and we obtain the right hand side as desired. So now we have already shown that AMGM inequality holds when n is a power of 2. Now suppose that n is not a power of 2. There exists some m which is a power of 2 and it's larger than n. So let alpha be the arithmetic mean of the terms x1 to xn. So we know that alpha is actually equal to this expression. We convert the denominator of the sum of all the terms from x1 to a1 to xan to be m, so that we can use the AMGM inequality for n equal to m, because we have already shown that AMGM inequality holds for all powers of 2. So based on the simplification that we have made, we can apply the AMGM inequality, and simplifying, we get the AMGM inequality for all m that is not a power of 2. We'll now be discussing a related inequality, which is the power mean inequality. So we define the p power mean of x1 to xn, where x1 to xn are all positive real numbers, to be the following expression. It is 1 over n of all the numbers raised to the power of p, and the whole thing is raised to the power of 1 over p. So we know that if p is less than q, the p power mean of x1 to xn is less than or equal to the q power mean of x1 to xn, and equality holds if and only if all the x1 to xn are equal. So there are some special cases of p where the p power mean has a special name. For example, when p equals 1, p equals to -1, we get the harmonic mean. As p approaches 0, m of 0 can actually be shown to converge to the geometric mean. As such, m0 can be explicitly defined to be the geometric mean, and it will still satisfy the generalized power mean inequality that we have mentioned earlier. If p equals 1, we get the arithmetic mean, and p equals 2 gives the quadratic mean.